start with this third lecture.
Thank you. So since this is the last day and I'm the last speaker from outside of Princeton, I would very much like to thank the hospitality of the Institute for Advanced Study, the leadership of Chiara, but also the staff member of IAS, accommodating 300 students plus some noisy lecturers. And Michelle, Sage, Lisa, Susan, and many staffs, and the technical staff back there. Last night at the dinner, I overheard people in the kitchen saying, "Last day." So I really appreciate their effort in accommodating us. So that means that you students should really take this advantage of this opportunity. So attending lectures, asking questions to speakers, but also getting to know each other, because friendships that are made on occasion like that will be very precious. So thank you for all coming. So I'd like to start talking about D-branes in the context of topological strings. So roughly based on my work with Yaron Oz and Jen In 960611. So there are two types of boundary conditions. Remember that in the case of A model, BRST charge are given by these operators. So if you have D-brane with boundary condition, you want to set up the boundary condition that preserves this BRST symmetry. So on the boundary, you want to impose the condition that G plus is either plus or minus G bar plus. You also want to preserve the U1 charge, so that means that the J has to be equal to J bar. In the case of B model, BRST operators are generated by G plus and G bar minus in my notation. So that means that the G plus has to be equal to either plus or minus G bar minus. Since the charge sign is flipped between left and right, so the identification should be J is equal to minus J bar. So, well, so far, yesterday we were talking about a case when the dimension of the target space is 3 because of some special feature of charge fermion number violation. But let me get back to the general N for now. So if you consider the simplest case, so the analysis of this type of D-brane has been done and very much in the last decade or so, and lots are known. Let me just talk about a very, very simple case where the gauge field on the branes are turned off, and you just have a metric background. And in the limit of semi-classical approximation, the leading order in alpha prime, if you solve this equation, in the case of A model, so I call that as A brane, if you have A brane wrapping on some cycle in Calabi-Yau space, namely you impose a condition that this boundary condition is taking place on a submanifold of the Calabi-Yau manifold, then what you can show is that these conditions implies that the scalar form restricted on this submanifold has to vanish. Now, scalar form is non-degenerate 2 form on the Calabi-Yau manifold. So you may think of this also as a symplectic form, just like in your phase space of dynamical system. So the submanifold where symplectic form vanishes is called Lagrangian. You should be familiar with the Hamiltonian formulation of classical mechanics, where a dynamical system is described by even-dimensional motion in even-dimensional manifold. Half of that is a coordinate and half of that is momentum. And if you restrict your space to the space of, say, coordinate, then symplectic form degenerate, and that's submanifold called Lagrangian. So the manifold, submanifold which support A brane has to be Lagrangian. So in particular, the dimension of this submanifold, the real dimension of this submanifold, has to be half of the real dimension of the total space, which is n. So Calabi-Yau 3-fold, the Lagrangian submanifold has to be 3 real dimensional. Okay? In the case for B brane, for B-brane, you can do the similar analysis and find that gamma has to be holomorphic submanifold in M. So you can derive that from semi-classical analysis of these conditions, which was explained in this paper. Okay. In addition, so these are the conditions for topological BRC symmetry on the worldsheet being preserved by the D-brane boundary condition. If we, in addition, want space-time supersymmetry with application of this type of topological strings to superstring in mind, just like Edward Witten talked about yesterday, and I will try to talk about later today, then you may want these D-brane to preserve also half of the space-time supersymmetry. Now, to describe space-time supersymmetry, what you're going to do is to bosonize these U1 current. Where these phi and phi has this two-point function. So that J and J has this operator product expansion. So if you bosonize it in this way, then the space-time SUSY generator contains a part which is like square root of n over 2, excuse me, I over square root of n over 2 times phi. So in the NSR formalism, you have a Ramon-Ramon vertex operator for space-time supersymmetry, and it contains this type of factor. So space-time supersymmetries are generated by these, and for the right mover, these are generated by these. Okay? So that means that, for example, in the case of A-brane, you would like the condition if the A-brane in order for A-brane to satisfy half of space-time supersymmetry, you would like the condition that this is satisfied for the left move between the left mover and the right mover. In order for this half of the supersymmetry to be preserved. From the geometric point of view, this is actually equal to holomorphic n forms contracted with psi's. And this is its complex conjugation. So therefore, this condition means that holomorphic n form restricted to gamma. Remember, gamma is n-dimensional submanifold, the real n-dimensional submanifold. Omega is n form, so you can restrict that to gamma, has to be equal to omega bar of gamma. So that's this condition. Okay? But then I remember that on the Calabi-Yau manifold, you have to have a condition that determinant of the metric is a product of omega and omega bar. This is actually equivalent to the condition that rich curvature of the manifold vanishes. So that means that this condition means that omega is actually volume form on gamma. So the Lagrange submanifold which satisfies this condition is called special Lagrangian. So the condition that A-brane satisfies, that preserves half of the topological BRC symmetry is satisfied if gamma is Lagrangian. But if you, in addition, your submanifold, if you want your submanifold to satisfy half of space-time supersymmetry, you need this additional special condition, and these are called special Lagrangian. Okay? And there is a corresponding condition for B-branes. Now, wonderful aspect of open string, which is described by string ending on D-branes, is that there is a field theory formulation to it. So there is a very nice paper by Witten about string field theory of this type in general in nuclear physics B2681986. I'm not sure whether you were born when this paper was written, but so there is a field theory formulation in the sense that you can actually write down Lagrangian and then just do the Feynman diagram as you would in any field theory, and then that would compute the loop amplitude of this topological field theory. Symbolically, you have a Lagrangian, which very much looks like a Chern-Simons Lagrangian, where phi is open string field described by open string Hilbert space, and then you have a 3-point function described by what is called Witten vertex. So, so then you can apply that for the A model and B model, namely open string on A brane and B brane. And in B model, in particular, since we know that the Kähler moduli of the B model is BRC trivial, so that means that you can take the volume of the Calabi-Yau as large as you like, which means that alpha prime correction is exact, and which in particular means that the string field theory reduces to ordinary field theory with local degrees of freedom. So B model open string is actually local field theory, typically. In the case of A model, it can be in general stringy. However, in exceptional situations where there are no compact 2 cycle, if M has no compact 2 cycle, then again it reduces to ordinary field theory. So we will discuss some of those situations now. So let's consider, say, A model on cotangent space of some 3-dimensional manifold. So let me get back to the case when the complex dimension of the Calabi-Yau is 3. So let's consider A model on cotangent space of some manifold M, where dimension, real dimension of M is 3. Okay? So obviously, well, this must be the case that you are familiar with in dynamical system. If you have a dynamical system for the motion of the manifold M, the phase space would be cotangent space of M, where the cotangent direction is a momentum. So clearly, M is then Lagrangian. So if you have M, and if you have a cotangent space to it, then D-brane wrapping on M should be A brane. So you can have n D-branes on M, and then this gives rise to UN Chern-Simons theory on M. If you apply Witten's procedure to write down open string field theory for this D-brane, and then, but however, we notice that there is actually no non-trivial holomorphic maps from 2-dimensional surface with boundaries ending on this M. You can, then you can show that, then from that kind of argument, you can show that this reduced to ordinary field theory. In this case, it's in Chern-Simons field theory. So this was also shown by Witten in his quite beautiful paper 9207094. Okay, so you have action for Chern-Simons theory with level k, ADA plus the 2/3 of A cube. Okay, so I have to tell you that here the string coupling constant, which I'm going to denote by lambda, is given by 2 pi I over k plus n. So string coupling constant is pure imaginary. Okay? So then also one should be able to expand. So in this case, so what open string amplitude look like? Where open string amplitude look like f of g and n, where you have a genus of the Riemann surface and n is a number of boundaries. Okay, so you have a Riemann surface with g handles and n boundaries, which is denoted by fg of n. And then you can sum fg and n by lambda of 2g minus 2. And then you have to have some kind of loop counting parameter, which I denote by t. And then you sum over g and n. And according to the correspondence between the open string field theory and the string theory computation, it should be equal to the Chern-Simons partition function with k and un for this three-dimensional manifold, where lambda is given by this formula and t is 2/5 coupling, which is 2 pi I n k plus n. So far, this has nothing to do with large n duality. This is just a reorganization of the open string amplitude in the field theory language. By studying this Qumran buffer, and I thought that it would be nice to understand also not the invariant of Jones polynomial and its generalization by Humphrey. And in fact, one can generalize this type of construction to compute not the invariant. And to do that, what you have to do, so this is my paper with Qumran buffer in 9912123. What you have to do is the following. So suppose you have a manifold, M, and suppose you have some kind of knot on it. Knot is just a map of S1 onto the submanifold. Now, how do you compute the knot invariant using the Chern-Simons theory, so we thought. And so I remember there are n branes, n D-brane wrapping on this submanifold M. So what we figured out is that you can do the following thing. You can consider a submanifold which is ending on M with this circle, but is extended in 2 more dimensions. Okay, so this is defined as follows. Suppose this loop is described by some kind of path. So x is a coordinate on M, and t is some one-dimensional parameter which parameterizes this circle. Okay? So then I consider the following submanifold C. So let's call that as L. Then I consider C of L to be defined as this path, but with conjugate momentum direction. Momentum direction is this cotangent direction, which is normal to the velocity of this vector. Okay? So for each, if you have this trajectory like that, this is a 3-dimensional vector. So if this gives you one condition for 3-dimensional vector P, so there are 2 solutions. So it's extended in 2 directions in P. So this is P, and this is X. So this gives you a 3-dimensional submanifold. This is also Lagrangian. This is also Lagrangian. So you can put D-brane on it. So you put n prime D-brane on it. Okay? Oh, by the way, so this is called the co-normal bundle. For each loop on this submanifold, you can define co-normal bundle on it. And CL has a topology of R2 times S1, because it's extended in 2 dimensions, and there is a circular direction to it. So in particular, there is a holonomy associated to it. If you have n prime D-brane on it, you can consider holonomy around this S1. So this is an element of U n prime. So what Cameron Buffer and I showed was that if you have such a setup, and if you consider partition function with this holonomy, then the partition function or partition free energy, according to the notation terminology yesterday, would be GH of summation of number of winding. So you can have, say, for example, H boundaries. So maybe I should have be consistent, and these are called H in my next note. Suppose you have H boundaries for this open string, then that boundary can wrap this holonomy several times. So suppose you have H boundary, each boundary can wrap the holonomy direction in various times. So that means that you can define open string amplitude with different number of windings for each of these boundaries. So you can consider the following, you can consider doing the following thing. This times trace of V to the D1. I assume V is in the fundamental representation, and then trace of V to the DH. So you can consider following this type of partition-free energy, and you can exponentiate it to make it into the partition function. And then we showed, Cameron Buffer showed that this is actually equal to expectation value of generating function of Wilson loop in the original Chern-Simons theory. So this is for the original Chern-Simons theory. And then this is for the probe holonomy, evaluated in the Chern-Simons theory. So you do the Chern-Simons partition function for this UN Chern-Simons theory and use this V as some kind of probe to it. So this will give you generating function. So this is generating function of Wilson loop. This is going to be a useful formula which I will use later in today's lecture. But before we get there, let me discuss the large N duality for this type of theory. So large N duality, as you all know, is a relation between open strings and closed strings. So you can have open string, which is typically related to gauge theory, to closed string, which is typically related to gravity theory. So ADS-CFT correspondence is an example, but we can actually have open string, a topological string version of large N duality, which we can actually discuss in much more detail the string theory aspect of it. So as an example that I showed over there, typically if you have open string, the amplitude depends on genus, but also number of handles, and that can come in various type of boundary conditions. So you can actually consider the following things. So suppose, for example, you can have open string. You can have D-branes, but suppose you have different kind of D-branes. You can have N D-brane wrapping on some cycle, M D-brane wrapping on another cycle. So you can have different kind of things. So you can have different type of boundary condition. You can say that N1 of the boundary end on D-brane of first type, N2 of them ends on boundary of second type, and etc. So the total number of boundary would be sum of these. Okay? So now I'm going to define the following thing. F G of T where t is some parameter, which I'm going to identify as a 't Hooft parameter later, is equal to sum of these boundaries. And I introduce 't Hooft parameter, loop counting, boundary counting parameter for each one of these boundary types. Okay? So this is a definition of partition-free energy. Now comes the conjecture. According to Het 't Hooft. The following is a conjecture, namely that whenever you have something like that, then there is a family of target space such that Fg of t is a closed string amplitude or partition-free energy on this manifold. So this will be a formulation of large-n duality. And so there are examples. So let's take an example from the A model associated to Chern-Simons theory that I just talked about. So in that case, Fg of n will be open topological string on T star, say, of 3 sphere. So let's take M up there to be 3 sphere. So then, without using large-n duality, that should be related to Chern-Simons theory on S3. So this statement has nothing to do with large-n duality, just a formulation of open string perturbation theory in terms of string field theory. But now comes the large-n duality statement, namely that if you consider Chern-Simons partition function on S3 for level k and n, so I remind you that level k and n are related to open string coupling constant and the 't Hooft parameter like this, then the partition function is given by e to the I pi over 8 n minus 1. I'm just writing this so that there is actually a formula known. Okay? And according to large-n duality, if this is dual to some closed string theory, well, first of all, excuse me, just by using the reformulation of Chern-Simons theory as open topological string theory, one should be able to reorganize this in terms of the partition function. So I want to remind you, this statement has nothing to do with large-n duality, just a re-expression of Chern-Simons theory partition function. But now you can ask, what is this thing? Does this thing has interpretation, has as a closed string amplitude? So this question was first asked by Vipul-Periwal, but was put into a more sort of convincing fashion by Gopakuma and Bafa in the beautiful paper 98-11131. So they show that actually you can sum over n, and you can write it in this fashion. Where this chi of g is -1 to the G minus 1, the Bernoulli number divided by some polynomial of G. And this turned out to be just Euler characteristic of the moduli space of genus G Riemann surface. And this is a Chern class of the Hodge bundle over that moduli space, whose formula is also known. And the relation between these and the explicit formula was actually conjectured by Gopakuma and Buffer based on the large N duality argument, and proven by Faber and Panda-Haripanda mathematically. This turned out to be the closed string amplitude on resolved conifold that we talked about yesterday. So this is a very clear demonstration of this conjecture where summing over the number of boundaries for open string by the 't-Hooft coupling actually turns the closed string open string amplitude into closed string amplitude, where T is now parameter of the target space geometry, in this case, the Kähler moduli of the conifold. Now, this large N duality also holds for open string with the additional D-branes. So here I explained that you can actually, so we were using the Chern-Simons theory formulation of open string field theory, where open string amplitude is expressed as Chern-Simons partition function. But you can also insert D-brane, additional D-brane on conormal bundle associated to knot, and then you can compute the knot invariant in this way too. So we can actually add these D-brane on conormal bundle on both sides of the large N duality, and these additional D-brane probes goes with the line of the large N duality. Namely, that so let me first draw the kind of caricature of cotangent space of S3. So this is S3 direction, and I put n D-brane on it. And in the cotangent space direction, so you have S3 to it, and then there is a S2 which shrinks to a point. So this is a caricature of cotangent space of T3 that I drew yesterday. And the conifold side is of this type without branes. So this is the resolved conifold. Where the 't-Hooft coupling, which is the size of this S2, is related to this 't-Hooft coupling. Okay, so now we can add D-brane to it. So you pick any knot over here. So I have a knot here. And then with the knot, I have a conormal bundle. And I put n prime D-brane on it. Then you do the large N duality. So then what happens is that there are actually corresponding branes on this side. So then you can show that knot invariant can also be expressed as a partition function on resolved conifold with additional probe D-brane. Okay? So this was also discussed in my paper with Kamran Buffer that I did. I cited over there. And this gives rise to a new expression for knot invariant. And I'm going to tell you later that this also has some interesting consequence to the idea of mirror symmetry. But I will come to that later. All these discussion leads to a very powerful way to compute topological string partition function on toric Calabi-Yau called topological vertex method. which I would like to discuss now. So this Radian duality between closed topological string and Chern-Simons theory allows us to compute Fg, the topological partition function, to all order in genus for toric-Calabi-Yau. Now, yesterday, I presented the toric-Calabi-Yau manifold. I defined them as T3 fibration. And then I drew some diagrams to describe the toric-Calabi-Yau as three-dimensional diagram. But alternatively, you can also describe that as T2 times R fibration by dividing the space in different way. And you also have a toric diagram associated to it. So basically, it's the same kind of toric diagram, but just projecting that three-dimensional toric diagram to an appropriate two-dimensional plane. So basically, you can use the same picture. But it is more convenient for the purpose of topological vertex and other applications. So let's look at the conifold. So if you have resolved the conifold, so that was my homework assignment yesterday, so I hope everybody has done it. So the toric-Calabi-Yau, toric description for the conifold has this charge assignment. So from that, you can deduce the toric diagram should be of this type. Okay? So I remind you that at each of these edges, one of the two cycles vanishes. So one of the two cycles vanishes, and this angle of this edge tells you which two cycles vanishes. So one cycle vanishes, the other cycle vanishes. In this direction, combination of them vanishes. On this corner, two of them vanishes simultaneously. So that means that on this corner, you have one cycle vanishes, but the other cycle is finite. On this corner, both vanishes. So that means that you have a small cycle, zero cycle, blows up, and then shrink to a point again. So that means that there is actually a S2 over here. And the radius of S2 is related to T. And that is this S2 over here. Okay? So this is the Radian closed string dual side, the resolved conifold. Now, if you have this kind of geometry parameterized by T, you can move T around and do various kind of things. So for example, you start with this resolved conifold diagram, and you have T here. And then suppose you shrink T to be 0. Then these coincide, and then you have this kind of diagram. Now you can consider stretching into the other direction. You can resolve. So this is a singular geometry where S2 shrink to a point. But you can try to resolve it in opposite direction, which actually correspond to T negative. And this is called flop transition. However, once you are here, there is another direction to go. Remember that originally, you had the T2 times R fibration over three-dimensional space. I'm just projecting it onto two-dimensional space. So you have actually one more direction of T2 fibration. So you can actually, once you have this kind of configuration, you can actually lift this degenerate fiber, the locus, in the third direction. So you can actually move this off like this. And then the closest place where they these two lines come together is expressed at dotted line. So now let's pause a moment and think about what kind of geometry we are talking about. So we have this three-dimensional geometry, and one cycle is vanishing on this side, and you have another cycle vanishing on this side. Now, what kind of geometry do we have along this dotted line? Okay? So, in fact, this turned out to be three-sphere. So let me try to convince you that this is a three-sphere. So our space is R2. But if you add a point at infinity, this becomes S3, right? And now let's imagine there is a handle body to it, just like a surface, a donut, but inside in it. So suppose you have donuts floating over here. There are 2 cycles on the surface of the donuts. But this cycle can be shrunk to a point. You cannot shrink this point you cannot shrink this cycle to a point going inside of the torus, right? So you can cut the donuts into this direction, but not in this direction. But you can actually shrink this cycle to outside of the torus, right? So if you have R2 and other point at infinity, then one of the cycles shrink to a point, the other cycle shrink to infinity. Okay? So this shows that actually the geometry of S3 can be described as a T2 fibrillation where one of the cycles shrink to a point in one direction, the other cycle shrinks to the other direction. So in fact, therefore, there is S3 associated to it. So the resulting geometry here is nothing but T star of S3. Okay? So this is actually this side of the geometry. So we can therefore describe the Largian duality in this type of procedure. You draw a toric diagram, and then you have a smooth toric geometry where you have Kähler moduli like that. You take the limit where Kähler moduli vanishes, and then you deform it in the third direction. Now you have open string wrapping on this extra cycle that emerges in this way. And this is a Lagrangian cycle on which you can draw. So the procedure is that you identify the number of D-branes on here as a 2-Hooft coupling on this side. Okay? So now we can apply this procedure locally to compute any topological string amplitude for toric Calabi-Yau. So let me describe that. So in order to explain that, let me do some examples. And the example I'd like to take first is an example of the local CP2 that I defined yesterday. This is getting complicated. Let's see, I can figure it out. This is more difficult than topological string, actually. Okay, did I do it right? Okay, so let's apply this procedure for local CP2. So do you remember the toric diagram of local CP2 that we discussed yesterday? Well, for local CP2, the toric diagram is like this. Local CP2, the toric diagram is like this, where you have the base CP2 over here, and there are 2 fibers. And the slope of these are described in this way. Slope of these edges are described in this way. So I'm just writing the slope in the Cartesian coordinate. Now, how I can use this diagram and apply this type of procedure to relate closed string amplitude here to open string amplitude here? As it is, it seems to be difficult to lift any of these lines. So the trick is to add more lines to it temporarily. So what you do is that, so here I need colored chalk. I need one more color. Yeah, here. So let's see if I can figure this out. So this is a toric diagram of CP3. I'm just adding color to show the slope properly. So there was this toric diagram of CP3, the local CP2. So now I add more lines to it. So these yellow lines are parallel to each other, and these blue lines are parallel to each other, and these red lines are parallel to each other. And now I have now 3 scalar moduli to here. Okay? So this is the extended version of local CP2 geometry. Okay? So now, once you have that, I can do this this open-close string transition for each of these places. Because now locally this looks like, so locally this looks like resolved conifold. This looks like resolved conifold. This looks like resolved conifold. So we can actually lift this like this. We can just shrink these to 0 and displace them separately. So there are 3 S3 connecting them. And then open-closed duality means that there are D-branes for these cycles where the original T1, T2, T3 are related to the number of D-branes in this way by the large N duality for each one of them. Now we can use Chern-Simons theory to compute this amplitude. So we have UN1 times UN2 times UN3 Chern-Simons theory on each of these S3. But in addition, there are open strings connecting these boundaries, because we will be doing full open string theory on this geometry with this number of D-brane wrapping on it. So nothing prevents us from thinking. So open string with both sides ending on each one of them gives you Chern-Simons theory. But open strings stretched between these D-brane give rise to bifundamental fields with fundamental representation in UN1 and anti-fundamental representation on UN2, etc. So you do the Chern-Simons partition function. Now what do you get? We have an answer which I wrote somewhere here. So this is an answer. So if you probe one Chern-Simons, if you probe, say, from the point of view of this UN1 Chern-Simons theory, bifundamental between these, you can think of this as a probe temporarily. And then compute UN1 Chern-Simons partition function first. Then, according to my computation with common buffer, you get this answer for UN1 Chern-Simons theory. Okay? So then, in the end, what you get is basically sum of n1, n equal 1 to infinity, 1 over n e to the minus n r, or r is the distance between here, times trace of un, trace of vn, and the expectation value of Chern-Simons theory for each one of these factors, and you with insertion of the bifundamental field over here. So the situation you have is that you have this kind of thing, and then you have open string going between them, like that. So this is, okay, so you do this for each one of these. So U has, so this is, here you are taking trace of a fundamental representation, say, of UN1. But you remember that this has, so this is just on this side. But you have the other, you have to remember you have the other side to it. Okay, so you do this for 3 factors. But then there is an interesting twist to the story, because you have this kind of three Chern-Simons theory on these three sides, and then you have an open string stretched between here. So you have open string stretched between here and here, and you have open string stretched between here and here. Each one of these is wrapping. So you remember the co-normal bundle has a topology of S1 times R2. So these open string endpoints can wrap on each one of these, right? And so you can ask, well, what's happening on the endpoint? And it turns out that because of the way that this resolution works and deformation works, the endpoint of this blue closed open string and endpoint of red open string are linked, like hop link. So therefore, from the point of this Chern-Simons theory, these two are linked. And so in the end, you would be computing actually the Chern-Simons partition function with this kind of linked open string, which you can compute. And therefore, in the end, everything can be expressed in terms of link invariant, namely that original topological string partition function for local CP2 can now be expressed as sum over representations for Chern-Simons theory over here, here, and here with product of link invariance for the hop link. Hop link is a link of this type associated things like this with appropriate factor. And you can do this exercise for any toric Calabi-Yau. Whenever you have a toric diagram, you can always add and subtract these edges, additional edges, and lift everything, recombine that, and reduce the computation to the computation of Chern-Simons gauge theory. So that's a method of topological vertex. I was hoping that I have time also to discuss. Let's see, I have until 11 o'clock. Is that the schedule? Okay. So I'm barely halfway through what I planned. So let's see, maybe I should just say briefly. So this is about open string, topological open string for B model. But there is also a beautiful story about topological open string. So this was a topological open string for A model. But there is also a beautiful story about topological open string for the A model, the B model. So I would like to talk about that. But before I get to that, I need to bring this thing down. So I told you that in the case of A model, the D-branes are Lagrange submanifold. And if you wrap D-brane on that Lagrange submanifold, then the resulting theory, open string theory, is a Chern-Simons theory on that Lagrange submanifold. And this gives rise to this topological vertex construction that I just discussed. So you can ask what happens in the case of B model. So in the case of B model, as we discussed, the required boundary conditions dictate that the submanifold in question should be holomorphic submanifold. So there is a good example for holomorphic submanifold. So for example, in the case of resolved conifold, the S2 is an example of holomorphic submanifold. So for example, if you have a resolved conifold, well, S2 and S3, then you can wrap n D-brane now on this S2 side. Previously, we deformed, we put n D-brane on the deformed conifold and gave rise to Chern-Simons theory. Now suppose we put n D-brane on the resolved conifold. And now this geometry has no complex structure. There is a Kähler moduli here, which is the size of S2. But since we are not talking about a B model, so the Kähler moduli is BRST trivial. So that means that this model has no parameter to it, except for the number of D-brane n wrapping on it. So in this case, it was shown by the director of this institute of a diagram and the Cameron buffer in 0206255 that the open string field theory is actually Gaussian matrix model. Which is just integral of UN matrix with Gaussian measure. And you can compute this thing exactly. You can compute this exactly. And find that this is equal to expressed by generalization of gamma function called Burns double gamma function. Where this is called Burns function, which is characterized by this type of recursion relation. Okay? So the dependence on string coupling constant is rather trivial like that. Now, as in the case of Chern-Simons theory, and in general for open closed string duality, we can expand this thing as the exponential of closed topological string amplitude. And it turns out that this has an expression like this. One can actually identify this as a B model closed string amplitude on deformed conifold. With the equation like this. So we are going backward in this case. So previously, we had deformed the conifold and put D-brane on it, and then took Lagrangian duality, and we went to the resolved conifold, where the size of the resolution is characterized by two-foot coupling. But on the other hand, here we started out with a resolved conifold and put B-branes on it. Now we went back to the deformed conifold. So we go sort of back and forth between them. Okay? So this type of correspondence is very useful and computationally very powerful. So I would like to discuss application of this type of idea to mirror symmetry. So if you have, so remember that mirror symmetry is a mirror pair of Calabi-Yau so if you have a mirror pair of Calabi-Yau M and N, then A model on Calabi-Yau manifold M is equivalent to B model on its dual Calabi-Yau manifold, say W. Okay, so suppose you have such a mirror pair. And then now it's interesting to see what happens if we add D-brane to it. Well, we can guess what can happen to D-branes. Because suppose you have A model on the manifold M. And suppose you wrap D-brane on its Lagrange submanifold. Well, in the case of A model, it has to be Lagrange submanifold. Now, if you go to its mirror partner W, then B-brane should be corresponding to the original A-brane. B-brane can wrap only on holomorphic submanifold. So that means that Lagrange submanifold in A model should get mapped to holomorphic submanifold for its mirror. I will discuss that towards the end of the lecture if I ever get to. I was planning to explain the relation to this kind of computation to four-dimensional supersymmetric gauge theories that Nati was talking about earlier. So if I let me go, then I will discuss that if I ever get there. So D-branes with mirror symmetry. So if you have A-brane on Calabi-Yau manifold M, then the mirror should be B-brane on its mirror pair W. So this is Lagrangian. So this should be holomorphic. In particular, the zero brane, which is a point on W, should be mirrored to some particular Lagrangian. So you can ask, what is the Lagrangian submanifold which is mirrored to a point of a Calabi-Yau manifold? Well, you can actually restrict your choice very severely. Because what is a moduli space of the D-brane, which is a point on W? Well, you can move this point around. So that means that moduli space of point should be the manifold itself. So that means that in particular, it's complex three-dimensional space. Now, you can ask what kind of Lagrangian can have complex three-dimensional space moduli space. It turns out that it has to be actually T3. You can show that if you have Lagrangian with dimension 3 moduli space, then it should be T3. Well, if you have T3, you have 3 cycles, so you can have holonomy of gauge field around each one of them. That gives you 3. But it's supersymmetric, so that actually becomes complex variable. So it gives you complex three-dimensional moduli space. And you can prove that that's the only choice. So that means that if you have mirror symmetry, and if you have a point or B-brane on one side, then its mirror partner should be family of T3. So you should have a T3 fibration. So this led the Strominger, Yau, and Zaslow to conjecture in their beautiful paper in 96-06-040 that any pair of Calabi-Yau manifold which are mirror partner to each other, if you have such a setup, then Calabi-Yau manifold M, which admits its mirror partner, must have a family of Lagrangian T3 fibration on it. So that the moduli space of the special Lagrangian 3-brane with this instanton give rise to the mirror W itself. Okay, so now actually, the standing of rather than proving this conjecture in generality, let me explain how it works in practice. How you can actually use this to derive mirror partner. Okay, so let's consider our familiar Calabi-Yau manifold, which is resolved conifold. Well, in this case, actually, it is non-compact. So it turns out that if you have non-compact Calabi-Yau like that, it doesn't admit T3 Lagrange, special Lagrangian fibration. It has to become non-compact. So rather than T3 fibration, you have to have R2 times S1 fibration. Okay, so how can we have R2 times S1 fibration? Well, that's our familiar friend. That would be our co-normal bundle would be an example of R2 times S1 Lagrange submanifold. So let's consider that our friend co-normal bundle. So let's choose, say, unknot, some cycle which is not wrapping with each other. And let's consider n D-brane on it. Well, so actually, I went ahead of myself. I'm sorry. So let me go back. So I'm going to use large N duality first. So here you have a resolved conifold. But topological string, closed string on the resolved conifold is equivalent to the n A-brane on P star of S3. Okay? So here you can have Lagrange 3 manifold associated to knot. That's our co-normal bundle. So that's co-normal bundle to unknot. Okay, so you have a T star of S3, and you can have n D-brane. And this is, of course, related to the Kähler moduli of the resolved conifold by the standard relation. Now, if you have co-normal bundle like that, then this co-normal bundle goes with a ride for the large N duality, and then you have a resolved conifold like that with S2 over here. And then there is a map of this co-normal bundle somewhere here. And this gives you the Lagrange submanifold, which is R2 times S1. According to Strominger-Yau-Zaslow conjecture, the moduli space of this R2 times S1 fibration, including this disk instanton correction, should give rise to the geometry of the mirror of the resolved conifold. Now, in general, computing the disk instanton and summing over them can be difficult task. But in this case, it turns out that since this is large N dual to Chern-Simons gauge theory, where you can do exact computation of knot invariant, so you can map this program into Chern-Simons gauge theory and compute it. And then you can derive that mirror should be equal to the following geometry, where this function f is given by this, where this t is a Kähler moduli. This is nothing but the expression that I discussed yesterday, the result of Hori and Buffer computing the mirror partner of the original resolved conifold by formulating it as linear sigma model and doing the T duality and vertex instanton computation. So this gives you alternative derivation. So yesterday I promised you that I'm going to explain the alternative derivation of this mirror partner. In fact, you can derive that by using Strominger-Yau-Zaslow conjecture and computing the disk instanton amplitude for the special Lagrangian R2 times S1 fibration. But you can ask, why did I choose unknot to describe this special Lagrangian fibration? You could have chosen other co-normal bundle. You could have, for example, on S2, S3, you could have, for example, trefoil. Like this. And then you can have co-normal bundle for trefoil. And play the same game again. So this was actually pointed out by Aganagic and Buffer a couple of years ago. And they actually show that for each one of these nodes, it can give rise to a candidate mirror manifold. For example, for trefoil, again, we can do exact Chern-Simons partition function computation and then use the large N duality to compute the disk instanton amplitude according to Strominger-Yau-Zastrow conjecture. It should give rise to the geometry of mirror partner. So they in this way derived more complicated geometry. Well, in view of time, I am not going to write that, but there is a formula for that. And amazingly, both of them actually, it has been checked that for all mirror Calabi-Yau associated to different nodes, if these, at least for those which can be drawn on torus, they all give rise to the same genus zero partition function. So look like in this kind of non-compact Calabi-Yau manifold, there is not one mirror, but there are infinitely many different mirrors associated to each of these nodes. Okay, so I have told you a variety of techniques that you can use to compute topological string amplitude. And is there any question at this point? Yes?
Explain once again in which sense your dualities are large n.
Sorry?
In which sense the dualities are large n?
Which duality?
Between open and closed topological strings. Because some of the formulas they look exact in n. Right? Your partition.
Large n duality is an exact statement for all n and lambda.
You never take n to infinity limit.
Well, I am taking n to infinite limit in a sense that when we actually do comparison, we are expanding things in 1 over n in the following sense. So for example, let's take this formula. Let's take this formula. So where this is open string amplitude, this is open string side, which I expressed exactly for finite n as a function of n, and the open string coupling constant lambda. So let's see. So here is the open string coupling constant lambda, and then size of n. So you have an exact formula for that. Now, so in large n duality, what you do is you expand this in this way, where T is a two-fifth coupling. Typically, when people say that it's 1 over n expansion, what they mean is that lambda is equal to 1 over n times t. Okay? So you can write this asymptotic expansion in string coupling constant as 1 over n expansion, because trivially, this is n to the 2g minus 2 times t to the 2g minus 2. So often, it is written that f of g is equal to t to the 2g minus 2 times this, the carry f of g is this solid fg. So then you can write this thing as a carry f of g divided by 1 over n to the 2g minus 2. So this looks like 1 over n asymptotic expansion. If you keep t finite and take large n, is the same as small string coupling constant. Okay? So in this case, this is an asymptotic expansion in 1 over n. And in that limit, it is verified that each one of these expansion terms has a topological string interpretation for closed string. So if I draw this, write this in curly notation, then this disappears, and there will be 1, and then this actually cancels out. So you might argue that this expansion makes more sense, right? Because now this is a pure number if you do that. And you may say that, well, this makes more sense because actually the dependence on the coupling constant was actually initially trivial, right? All other term depends only on n. And so indeed, I mean, this all higher genus amplitude is just number, and which is an expansion of this thing, okay? And only coupling constant dependence is here, genus 0 and genus 1. So you might argue that this carry f makes more sense in that sense. And if you do that, it can turn into 1 over n expansion. Does that make sense? Okay. Any other question? Yes?
Well, actually, I have a comment on that, though.
Yes, please.
So I think that the basic duality between the resolved counterfold with flux and the deformed counterfold with D-branes
Yes.
is supposed to be true for every n from 1 except 0.
Yes.
From 1 to infinity. But when you introduce a knot and use the duality to study a knot, I believe you're following the knot through the geometric transition. And that, I think, is believed to be only true for any given knot for sufficiently large n.
Yes.
The reason is that the knot is being treated as a spectator. The Lagrangian submanifold associated to the knot is being treated as a spectator in the duality, and you're using the same duality you had without the knot. If n is small, probably the knot can influence the duality.
Thank you. Yes. In fact, for finite n, there will be some constraint on these kind of invariants. For example, here, so in the context of our discussion, for example, we treated all these as if they are totally independent of each other for all n. But for finite n, there will be a relation between them. And I guess that's one of the aspects that you are referring to. Namely that here I treat it as if these coefficients are all independent. And so I guess there was some more appropriate formula somewhere, but I raised them.
Well, I don't know exactly what's supposed to be true. I'm very sympathetic to the questioner.
Yes.
I was tossing out the possibility that for every given knot, this duality is valid for sufficiently large n.
I agree.
But I don't know if that's actually the correct statement.
Well, I do not know what happens for finite n with knot. Here I'm explaining how it works without knot. Yes, indeed. Okay, so in the remaining 10 minutes or so, I would like to discuss the application of all these to type 2 superstring compactified on Calabi-Yau manifolds. Okay, so thankfully, Ed Whitting already had some discussion yesterday, so I can borrow some of his talk. So you consider type 2A or 2B compactified on that Calabi-Yau that we have been discussing in the past 3 days. And this gives rise to theory on R3 with n equal 2 supersymmetry. And then you have supergravity multiplet and vector multiplet and hypermultiplet. Supergravity has graviphoton in it, which plays a central role in Edward's talk yesterday. You have a vector multiplet. In the case of type 2A, the vector multiplet is associated to scalar moduli. Type 2B, vector multiplet is associated to complex moduli. And in addition, you have a hypermultiplet, which in addition to Calabi-Yau moduli, also contains so-called universal hypermultiplet. Here, I pay attention to vector multiplet. And then you have, those are described by super multiplet field. So you have a chiral superfield, which start out with the moduli and other field. And then you have a gravity multiplet, which start out with graviphoton field strength. I guess Edward used a notation T yesterday. And then you have some higher term, which includes the Riemann curvature. Okay. Now, among the low energy effective theory terms that you'd be interested in these compactifications are F terms. And F term can be expressed thoroughly by holomorphic integral in the superspace. So you have W square to the 2G times some function which depends only on T. And you can expand it, and it turns out that this is related to genus G topological string amplitude. So I would like to roughly explain why something like that can possibly be true. Okay? So remember that when you have topological string, you have to do topological twisting. So topological twist is equivalent to introducing background gauge field on the string worldsheet and couple it to the U1 current. A bar J plus A J bar, and choose this A to be equal to half of the spin connection. That's a prescription. However, if you have worldsheet gauge field, then the U1 current is no more conserved because there is a chiral anomaly. So in this case, the chiral anomaly is proportional to n times r times square root of g, where n is a complex dimension of the target space. In the case we are interested in, it is 3. There are various ways to formulate it. One way is, so I erased it, but at some point I was bosonizing the U1 current like this. Then if you do that, then this equation becomes del del bar of phi is equal to n times r or something like that. So square root of n probably, because there is a square root of n to it. So that means that this a bar times j now becomes 1/2 of spin connection times del of j, and j is that. So this gives rise to the coupling of this scalar field phi to the curvature. Namely, the effective action for phi will be del phi, del bar phi, plus additional coupling to the curvature. So this is an effective action for the bosonized U1 current. Now, if you have a genus G Riemann surface, we know that if you integrate the scalar curvature, it should give you Euler characteristic of genus G surface, which is equal to 2 minus 2G in appropriate notation. So that means that, in fact, you can choose the approach. So since we are talking about conformal field theory, so the actual choice of local metric does not matter. So you can choose a metric as you please, provided that complex structure and these topological characteristics are not modified. So in particular, you can write this as sum of delta function. If you write it in as sum of delta function, then this term in the action give rise to product of local operators. And the modular integral give rise to basically integral of these insertion point. This is nothing but the contribution of compactified part to the vertex operator of Ramon-Ramon type. Namely, these are Ramon-Ramon important component of Ramon-Ramon vertex operator. So if you have a string theory in NSR formalism, you have NS sector and Ramon sector. Ramon-Ramon sector give rise to, in particular, graviphoton that we are talking about here. So the graviphoton vertex operator has to have this type of component to it. So this naturally shows why topological string amplitude has anything to do with graviphoton scattering amplitude. It requires more work to figure out that it is exactly topological string amplitude. And the state of art is that it requires identities of theta function in some gory detail. I think this relation between topological string and graviphoton amplitude is so fundamental, so there ought to be a nice, intuitive, straightforward derivation of the relation between this term here and topological string amplitude. This is true statement. You can derive it, not beautifully, and I hope there will be a beautiful derivation of this statement. Anyway, so if you take this as a fact, then you can do various computations. So for example, f0 of t in particular, is the prepotential for n equal to vector multiplet. So that means that actually you can use this procedure to solve some low energy dynamics of n equal to supersymmetric gauge theories. So for example, let's take our friend local CP2. So local CP1 times CP1. So the toric diagram is of this type. And so this was another exercise, that homework exercise that I assigned to you yesterday. So this is the charge distribution. Now, if you take this non-compact Calabi-Yau manifold, this is non-compact. So that means that the Newton constant is 0 in 4 dimensions. So low energy effective theory is a field theory if you take an appropriate limit to it. And in fact, in this case, it is actually n equal to pure SU2 super-Yang-Mills theory. Okay? And then you can ask, well, what is the geometry associated to this that captures open string dynamics to it? Well, you can compute the mirror to it. Mirror can be computed exactly using this SYZ duality and mapping it to Chern-Simon theory. And then you can derive that mirror is this, of this type. Because you can transform this into Chern-Simon computation, sum over this disk instanton correction exactly, and then identify mirror. And it turns out that in this case, this is actually nothing but Seiberg-Witten curve. So you can derive the result of Seiberg and Witten by mapping into the computation in this local CP1 and using the topological string method to identify the mirror curve exactly. I have 0 minutes, so may I have 1 minute? A little bit, thank you. So I just wanted to, so Edward asked me over lunch or dinner, I forgot, why that Hooft coupling has to be flat connection. I'm not sure I'm going to be answering that question in 1 minute, but I'm going to say something which may be related to that question, which has to do with open string. So remember, in the case of open string, you can consider the sum of boundaries with some generating function. If you have actually D-branes, and then you can also have type 2 with D-brane, then you have an interpretation of S as low energy superfield, which has to do with product of gravitino field. Okay, so I don't have time to explain that, but this is again, even if we have open string, you can interpret it as a part of low energy effective F term, where S is related to product. So this is sometimes called the Grubor superfield, and but it's basically computing scattering amplitude of gluinos. So then, if you have n equal to F term, you can compute using this some F term. For example, for G equals 0, it gives rise to now a superspace integral of Ni del F I del Si 0. This may be familiar from the talk lecture by Nati Seiberg. So you have a Yang-Mills kinetic term, and then there is an effective term that is related to this low energy effective action. Very often, if you have open string, there is a closed string dual with fluxes associated to it. So you have a flux dual. Okay? So then you go to large N dual, and you have a geometry with fluxes in it. And in the original type 2 string description, then you have n equal to superfield, which is associated to the moduli for that cycle. And then there is a term associated to flux. So this is a flux. And this is a period associated to the cycle. For example, in the type 2b, this xi is a period integral of holomorphic 3 form associated to the cycle where the flux is going through. So then you can compute n equal 2 effective theory using this. Now you have 4 thetas, but then you integrate. This is actually 1 and 2, excuse me. So then this actually computation gives rise to a term like this. So if you compare both hand sides, you recognize that this contribution to the flux is taking form which is very similar to term like that, provided that you make identification that this Si is equal to Ni. So this is sort of one piece of evidence. Xi, excuse me. So this is a Tofuft coupling, and this is a corresponding period in the geometry. And the ratio of that would be yeah. That's well, I have minus 2 minutes. So, so in particular, yes, thank you. So in particular, for example, if you have resolved the conifold again, F0 would be equal to 1/2 of x squared log x. Oh, it must have been somewhere up there, but I raised when I discussed the matrix model. Remember, F0 was of this type. If you look back your note, you recognize that. So then if you apply this procedure, you find that n times del f del s give rise to n s log s minus 2 pi I tau of s. And this is nothing but Veneziano-Jankiewicz superpotential that appears in the lecture by Nati Zyberg. And this was pointed out again by the director of this institute, Digraph and Buffer. So you see that there will be the topological string computation has lots of beautiful connection to a variety of physics that were discussed during this summer school. So sounds like this is a good place to start. Thank you, and thank you for extending my time also. Thank you very much for everyone.